So now you see my iPad, and I have already prepared some images to illustrate an application, which is a nice ski day ahead. So this picture that you see here, I took not this year, unfortunately. We had a very bad winter this year in terms of snow, but this was from last year. So I woke up and saw it's a super nice day. So I was about to prepare a ski trip using my new cross-country skis, these Carhu skis. And one key challenge for having a nice ski trip is to use the right preparation of the skis, in particular, to use the right wax. And it turns out that there are different types of wax which are more suitable for different temperatures. So the right wax depends, in order to choose the right wax, you need to know the temperature. And typically you need to know the temperature during the day, because when you start in the morning, you are fit and everything goes well, but then around lunchtime, if you do a long trip, then it gets challenging. And then you better have the right wax for a good skiing experience. So the key problem could be, or in order to model this as a machine learning problem, we could say we would be interested in predicting the maximum daytime temperature in order to be able to choose the right wax. Okay, so one data point is some ski day. What could be features of a data point? Any ideas? What could be characteristics of the data point that I can measure easily? So I wake up, I see in the morning, I look out the window in the morning, and I see a nice ski day ahead. So what can I measure easily in the morning? Well, I can measure easily, for example, you see here, there's the current temperature. Yes, very good point. So the current temperature means, since I'm in the morning, since I look out of the window in the morning, what I typically know is the minimum temperature of the day. Because in the morning, it's typically the coldest of the ski day ahead. What else could I use as features, as characteristics of the ski day ahead? Yeah, the current weather situation, clouds. Yes. So the snow, how much snow, depth, I could use as a feature. And yeah, the minimum temperature, for example, it depends where. The minimum temperature of the ski day ahead. So I know in the morning the minimum temperature at my location. So I could also say another feature would be the minimum temperature, so the morning temperature at all nearby weather stations. Any other idea for features that characterize the data point? So one data point means some ski day ahead. And this might sound a bit strange, some ski day ahead. This is not really something concrete. And the point here is also to show you data point, the concept of data points is highly abstract. So a data point can be anything, almost anything and everything. So it's very versatile, and this is in some sense, this is useful because we can apply the concept of data points to almost any aspect of everyday life, for example, the ski day ahead. But on the other hand, this means, since this is so abstract, we need to make it concrete for the particular application. So we need to work out what is the data point exactly here? What are the characteristics, for example, the features? And as we now already saw, there are many, many features. So we typically have a lot of features of a data point, everything that can be measured or determined easily. And in principle, we can also say as features of the ski day ahead, we could use, for example, I wake up in the morning and open my Google and ask for the weather forecast. So the weather forecast that you see here in the morning, all this data here that you see, this -3.9, -5.2, -5.2, these are all features. This is all data that you can read in easily, for example, via Python code that accesses Google and reads out the results for the query weather. So this is in German, I'm sorry, weather. So you can do this with your Python notebook. You can read in the weather forecast by Google. And this is all data you can use as features. Yes, another comment from one student, we could use the historical values of previous days or previous years. And to this, we can query the Finnish Meteorological Institute, or FMI, which provides the observations for the last 20 years or so. So let's see, download observations. So you can choose the parameters. So these parameters mean the features that we're interested in. So we could use as features the radiation, properties, how much sunshine, or let's say we are not too greedy, we only use as features the minimum and maximum temperature of the day. And then we can go back, we can use historic data. So let's see how far this goes back. FMI, the Finnish Meteorological Institute, has data until, oh, this goes back quite a lot, 1880. So we can download all the daily minimum and maximum temperature from 1880 till now. Yeah, and then we can not only download the data for one station, but for any station the Finnish Meteorological Institute operates. So, but let's choose one which is close to me. So I live near Vuosaari. Let's see if we have something here. Look up. Yeah, here are all stations which we could use, and it's up to us which stations we use. So what we do now is feature selection. We select which observation station provides the best characteristics or the best features for our problem. And since I live near Vuosaari, I should choose, so okay, this is now a bit slow, but I should choose the station here in the south near Vuosaari. But I did this before already, so you can and you can also do it in a Python notebook. You can query this FMI data in a Python notebook. And I've done this before, and here's what I got. So you get a CSV file with all the historic recordings of maximum temperature and minimum temperature for each previous day. So here this was the 29th of June in 2013. So this one row corresponds to one day. And we could say this one row corresponds to one data point. However, this is only one option. We could say we use, for example, for one data point, so one data point is a ski day ahead, but as features, we could also use all the minimum and maximum temperature from the previous day too. So we could say one data point corresponds to two rows in this CSV file. So this is completely up to you what you choose as features. And not only what you choose as features is up to you, also what you consider as a data point is up to you. Okay, so that's about features. What could be the label? What could be the quantity of interest of a data point? I have already give you an idea what could be the quantity of interest. So what could be the label? This is all features. So this is a feature vector. x1. So let's say this minimum temperature is called x1. This is the cloudiness, or the amount of clouds is x2, x3 is the snow depth. Minimum temperature at all nearby, or at one nearby station, is x4. So we can stack all these features into one feature vector, which characterizes a ski day ahead. So what could be the label, the quantity of interest? What could be the quantity of interest? Well, if we want to know what is the right vex, we would be interested in the maximum temperature. Temperature during the ski day. Okay. So this is y. This is our label y. And this, let's say we model it as a number, so y is real valued. And what I would like to have, and maybe some of you know, if such an app exists, a high precision prediction of the maximum temperature based on the features. So this is what we're interested in. And in machine learning, what this is, this predictor, this is called a hypothesis map, or a prediction map. So we want to predict, based on the features, all the data that I have in the morning when I look out the window, or when I use my Google weather forecast, all the features I want to use to make the best guess or prediction of the map of the label y, which is the maximum temperature during the ski day. So what the machine learning problem here is, find a map, let's call it a predictor map, H, such that the output, which we call y hat, this is the predicted label, this is the output of the map, is a good approximation to the true label, the true or the actual maximum temperature during the ski day. So, but this label I do not know for today. I do not know what the maximum temperature will be today, unless I have observed today completely. And this I can only do afterwards, tomorrow. However, I can look back in time, so I can look at data points corresponding to previous ski days. So I can then use this data from the Finnish Meteorological Institute to create a labeled data points. So each data point has a feature and a label. So this is the first data point, and let's say I have up to m such data points. So what is this here? This is the minimum temperature of day 1, and this is the maximum temperature of day 1. This here is the minimum temperature of day m. So this means these data points are obtained by m such rows. Okay, for each row I look at the maximum temperature. This is y1. The minimum temperature, this is x1. And here the last one, let's say I pick up only these data points, ym, xm. Okay, so I can create a bunch of labeled data, or I can obtain a bunch of labeled data points. And so getting labeled data is easy for time series data, or for data that is collected over time, because we can look back into the history and know in hindsight what the label is. And based on the relation between features and label, in hindsight, we make a prediction, or we learn a predictor to tell us the prediction for today. So, but for today, we don't know. We don't know the true label for today, so we can only get a prediction for today. However, we can try out different predictors by looking how good would they have predicted the maximum temperature for previous days. So if we now plot here as a scatter plot, so a good idea to start a machine learning problem or to start working on a machine learning problem is to visualize the data. So we visualize the data in a scatter plot where the horizontal axis is the feature and the vertical axis means the values or represents the values of the label. And so from FMI, we get such data. And then what we do, we try to learn a predictor. So we try to fit a curve that represents a predictor function. Let's make it red. So this here is a predictor. This is a certain function that reads in the feature and outputs a predicted label or a prediction for the label. Different. So here we have a predictor. It's just a function. So for any possible value, let's say for x equals 2, we can evaluate the predictor and get a prediction for the maximum daytime temperature. So all we need to do now is just optimally fit this predictor function to the training data set. So minimize these errors. And the question then is how to measure the errors. So what is a good measure or loss function? How to measure or quantify errors? Because we typically will have a non-zero estimation or prediction error. We will have for this, let's say we have a data point for illustration. We have a data point here with some minimum temperature or feature value xi and true value for the label yi. And if we apply the predictor for this data point, so what we do, we evaluate the function for this feature xi, and we get the prediction here, which is y hat I. So this is the predicted label of ith data point. And this prediction is based solely on the feature xi, nothing else. Because a predictor is nothing but a function that reads in the feature value and outputs a predicted value for the label. However, this predicted label, as you can see here, is different from the true label. So this is the true label. So there's a discrepancy. This y hat I, the predicted label, minus the true label is not zero. So we can illustrate this difference here as this distance. So how should we measure this error? How can we quantify this prediction error? Any suggestions? What loss function could we use to measure this prediction error? Well, maybe one of the most popular choices is the squared error loss. Which just is the square of this prediction error. And the machine learning problem would then be minimize, and we not only have one loss, but we have a loss for each, we have a prediction error for each labeled data point. So we have to minimize the average loss over all labeled data points. Over some set of predictors. And one key component of any machine learning method is the subset of predictors that we want to consider. Because if we allow any function, if we allow any predictor function, this optimization problem is basically meaningless. It's trivial because you can always minimize the training error by choosing a function that perfectly fits through all data points. Okay, this one not, but I have to draw it a bit different. We can always find a function extremely wobbly, but who cares, that perfectly fits the training data and makes this average loss or training error, so this is the training error, 0. Therefore, we need to restrict the predictor to belong to a subset of functions. Restrict the predictor function or predictor map to belong to a subset of maps that map the feature values to possible label values. So in this case, this would be a map, any map from real numbers to real numbers. So does anyone remember how we call this subset of maps? Yes, very good. So one student correctly said or commented that this is called the hypothesis space. Hypothesis space of a machine learning method. There are different choices. So one choice is maybe the most simple class of, or some most simple hypothesis space is given by linear predictors. So a linear predictor is a map of the form weight times feature. So with a linear predictor, we can represent, let's have a new plot here, some data points, labeled data points, and the linear predictor can represent only predictor maps that are end up as a linear curve in this plane spanned by the features and label values. So we only can change the weight here, which is essentially the slope. So we can change the slope of the curve, but nothing else. And then we might think, okay, this best linear curve might not actually be one that goes exactly through the origin. So we might add here another parameter. Let's call this B, which is an offset or intercept. So adding this parameter gives us more flexibility and makes the space larger, the hypothesis space larger. For example, we can now also implement a shift, a vertical shift of the predictor function. This makes sense if the data points are not centered or don't have a zero mean. However, I mean, it depends on the application. So if we look at the temperature data, you can download FMI data and study if it's a good idea to require the intercept term to be 0. So do we expect if the minimum in our application, the feature was the minimum temperature during the day, and this was the maximum temperature during the day. So do we expect that if the minimum temperature is around 0 in the morning, that also the maximum temperature will be around 0? Or is there a consistent shift in the maximum temperature relative to the minimum temperature? Does anyone have an opinion on this? Should we have an intercept term for such temperature data? Yes, so one student commented yes, and I agree, because if you look at the temperature recordings, then you will clearly see there is a shift. So the maximum temperature is not directly proportional to the minimum temperature. Even if the minimum temperature is, for example, -10, the maximum temperature in spring and fall, it will go up to 0 or over 0. Okay. So these are the 3 components, by the way, of machine learning. So first component, data, data points. So a data set, data is as a collection of data points, which are elementary units of information or elementary units of data, which are of similar type. In our case, one data point corresponds to some ski day ahead. And each data point is characterized by features, which are characteristics, any measurements that you can obtain easily for a data point. And the data point also is characterized or often characterized by some quantity of interest, which we call label. And this is the characteristic we would like to know, which we typically cannot determine easily. And that's why we develop a machine learning method to predict the label, to get a good guess or an educated guess what could be this quantity of interest or a label of a data point. And how do we do it in machine learning? Well, we try to find a predictor map that belongs to some subset of functions, for example, subset of linear functions, and we try to find the best such function or predictor map out of this hypothesis space based on some data points for which we know the labels. So for these data points, for the historic weather data, we know the label, we know the y coordinate, we know what the maximum temperature was during that day. However, this is a day in the past, but we assume that the behavior or the relation between features and labels is the same for the days in the past as for the days or for the current day or the days in the future. And this might not always be true. So this is a modeling assumption. Okay, so now that we have these 3 components, which are labeled data points, x, y, so with feature x, y, and label value yi, we have chosen a hypothesis space by using only functions of the form weight times the feature plus some intercept term. So these are the tuning parameters. So this we can tune. The weight, which is the slope of the linear function, and the bias, which is the offset. This we can tune. And we tune this in order to minimize the average loss or training error. This is sometimes called training error. So we want to solve an optimization problem. We want to minimize the training error over all choices of parameters W and B, which are the parameters of the predictor map. So we want to minimize this average loss, and let's say we use the squared error loss, which is true label value minus the predicted to the power of 2. And here we can insert what is the predicted label? Well, we use a linear map. So the predicted label is W times xi, the feature of the ith data point, plus the intercept term. So if we insert this, we end up with the optimization problem minimize over W and B, 1 over M yi minus, here's the predicted label, which is W times xi. So it's a number, it's not a vector, plus B to the power of 2. So machine learning, mathematically, machine learning amounts to solving optimization problems. And this optimization problem is obtained by the problem of finding the best choice for the parameters in order to minimize the training or the average loss over some training data points or training error. So machine learning methods, in some sense, are optimization methods. And the nice thing about this particular choice or this combination of linear predictors and the squared error loss is, when you look at this optimization problem via the cost function, let's say the objective function, let's denote this function. This is a function, some function or cost function of the parameters W and B. So if we look at the shape of this function, this cost function that we want to optimize, this has a very nice shape. So choosing a okay, let's first discuss why this is a nice shape. This is a convex function, and moreover, it is a smooth function, or we call it differentiable. What does that mean? Convex means it's bowl-shaped, so it has one unique optimum. So there is the minimum training error, and it's achieved by one particular choice. Let's call it W hat, B hat. So these two numbers achieve, when plugged in here to this optimization problem, achieve the minimum value. And differentiable means, or another term is also smooth. Smooth because you can approximate this function at each point by the tangent at the point. So you can compute the derivative or the gradient in general, the gradient, or let's say the partial derivatives of this function with respect to the parameters. And these partial derivatives allow you to approximate this function, this objective function by tangent or by linear functions. And these approximation properties that we have for differentiable functions allow to optimize or to find the optimal value in a very simple and extremely powerful manner. Yeah, does any one of you know how we could solve, how would you solve this optimization problem? So I give you a bunch of numbers, which are the labels and the features of some data points. So you get these numbers from FMI. So you read it out from here. Here you have the concrete numbers. I give you these numbers, and I ask you to find the value W, the real number W, and B, which minimizes this expression here. Does anyone have an idea how to find these optimal choices for W and B? Does anyone have an idea? I mean, related to this problem. Well, one super simple and powerful method or scheme to compute this optimal W and B is called gradient descent. What does gradient descent do? Well, if you want to find the minimum of such a convex and differentiable function, you start with some first guess, compute the gradient, and go down the gradient to get the next best guess. And you go down the gradient to get the next guess. And you repeat this until you are close enough to the optimal. So in formula, how does this look like? We start with some initial guess, or with initial, let's say guess. We can choose this randomly or set it to 0 for W hat and B hat. So these are the current approximation of optimal parameters. So the optimal parameters are W hat and B hat, shown here. So they correspond to the choice for the weight and the intercept that minimize the training error. So they are there. This is a mathematical result that there exists, at least we know there exists an optimal value for W and B. So that's a good start. But how do we know? How do we find out what the values are? Well, there's gradient descent. We start with any guess and we update, we get a new guess, WK, so for the W's, by looking at the old guess and going down by some step size, the partial derivative of this objective function evaluated at the previous guesses, because we have two, and adding to the previous guess. So this is the gradient step. This is the old guess. And this is the new guess. And we repeat this. So we then plug this in here and here. We get a new value here again. Then we go in circles, so to say. And we construct a sequence of estimates. So we start with the initial guess. We implement the gradient step. We get a new estimate. We implement the gradient step. We get a new estimate. And it turns out, if we do this sufficiently often, we call this a maximum number for iterations. So for example, for W hat, after 1,000 iterations, it's a very good approximation. It can be shown under certain conditions that it's a good approximation to the optimal weight. Okay. So we can compute the optimal weights easily for this loss function, which is convex and differential. But the important point here is this loss function, this expression here, depends on the choice of loss function and on the choice of hypothesis space. So how do the predictor functions look like? So for linear predictor functions and squared error loss, we get a nice problem that we can solve using gradient descent. And by the way, gradient descent methods or variants of gradient descent are the main method to fit or to do deep learning. So deep neural networks are again functions, nothing else but predictor functions that depend on some parameters, which we call W, but they don't depend on one parameter, but on billions of parameters. So a neural network involves billions of parameters. And what deep learning methods do is, well, they try to find the best choices for these weights, and they do it by variants of gradient descent. So everything that you hear currently about cool deep learning applications, it's based on using gradient descent. Okay, so there was one question from a student, which is, what are the alternative hypothesis spaces we could use for this data set and why we would choose particularly linear predictors. So one reason why we would choose linear predictors is because we can solve this optimization problem easily. And this is a strong, a big reason, because you can choose very fancy hypothesis spaces, but if you cannot very efficiently and fast fit these predictor functions to data points, they don't help you that much, because you typically only have a limited time. And you see this now in this corona crisis. Many of the actions of the policymakers depend on predictions. They depend on predictions, for example, on how many people will get infected, how many people will end up in intensive care, and when do we hit the capacity of a healthcare system. And these predictions, they are obtained to some extent by fitting models to data, to historic data, but you cannot take too long time to fit these models, because the politicians need the insights today before the next press conference. So that's why linear functions are handy, because we can optimize them easily. So the question was also, what are alternative hypothesis spaces? Well, we could look at another hypothesis space, which is polynomial predictors. Polynomial predictors, which are of the form polynomial, as the name suggests, and the weights here are the coefficients of the polynomial. So let's say up to a maximum degree n. So the coefficients of the polynomial are the weights. And already this hypothesis space of polynomial predictors with some degree or maximum degree n, we typically need to limit the degree because we only have finite computational resources. Already with this hypothesis space, we can perfectly fit any data set with less than n. So for if the number of labeled data points, so this is the training size, is smaller than n, the degree of the polynomial, we can fit any data set perfectly. This follows straightforwardly from a fundamental theorem in mathematics that you can, given m data points, you can fit perfectly a polynomial of degree more than m. In the simplest case, look at 2 data points. At 2 data points, so n is 2, and let's say n, or even here in this case, you see it's already for n, n equal 2, which would mean every constant function, every linear function, and every quadratic function. So here we can already fit perfectly a curve. A linear function, you can, for 2 data points, you can find always a linear function which perfectly fits it. And polynomial predictors generalize this to m data points, to more than 2 data points, simply by using a sufficiently high degree of the polynomial. So you need to be careful when using polynomial predictors, because if you choose a too large degree of the polynomial, you will get the following. When you minimize the training error, so you do this minimization, where h is a polynomial, what do you think you get if the degree with degree n larger than m? M is the number of data points, or training size, and n is the degree of the polynomial. So whenever you do this optimization problem for polynomials with too large degree, this will be trivial, because this will be 0. Simply because you can always find at least one polynomial that perfectly fits the training data. And this is also the case. So another example for hypothesis space is given by artificial neural networks, which contain as a special class deep neural networks. So deep learning is based on a particular choice for the hypothesis space. And in deep learning, what we do, we start with the feature, and then we use a flowchart representation of simple computations. So this diagram here, these edges represent, for example, multiply the feature with this weight W1, or multiply this feature with this weight W2 here, and then process it using neurons. So each circle here is a neuron. And what a neuron does is very simple or stupid in some sense, so not very complicated. So it computes the weighted sum of all its inputs. So it computes internally, let's write it out, W1 times X1 plus W2 times X2 plus W3 times X3, computes the weighted sum of the inputs using the weights along the edges, and applies a nonlinear function, which we call activation function. And this activation function can be, for example, just a thresholding. So if this sum is larger than 0, you are here, so you output 1. And if it's smaller than 0, you output 0. So a neural network is nothing but a concatenation of these simple computational units. And in the end, what it provides us, or what does it deliver? It delivers just again nothing but a mapping that is parameterized by many, many parameters. And this mapping, or this predictor map for artificial neural network, how do we implement it? Well, we implement it using this flow diagram. So we take the input feature, multiply it with this weight here along this edge, apply the nonlinearity in each neuron, output the result of the nonlinearity, and then continue with weighting the results, and so on and so forth. So, but this is a topic of an entire course. So there are a course at Aalto also called deep learning. And actually we will soon release a follow-up course of this course, which you now take, which will be called deep learning with Python, which might be a good follow-up course after this course. So also for this choice, so this artificial neural networks are a particular hypothesis space. So it's a hypothesis space made up by all predictor functions that can be represented by such a flowchart. And also here, this space of functions is so big, so vast, that it contains for sure a function that will perfectly fit the training data. So also here, we will get, if we minimize the training error over all predictor functions that are artificial neural network, what we get is training error 0. So when you download or when you use a library for deep learning, you will, maybe the first thing that you will observe is that you can fit the training data that you have, for example, this Finnish Meteorological Institute data perfectly. So the training error would be 0. However, you need to use these results or interpret these results with care. What could be the problem? Or do you think it's a good idea to use a hypothesis space that is so large that it can perfectly fit the training data? So is it good if you have 0 training error? Yes, one excellent comment. No, it's not good because I have tried out once. I have downloaded FMI data. So X was the minimum temperature of the day, Y was the maximum temperature of the day. I had some data points. And then I thought, okay, I wanted to try out using deep nets deep neural networks in Python. So I trained a deep neural network, and what I got was essentially this. Okay. And here it was, I think here it was around 0 degree. And here it was around, I think the data point here was 15 degrees. And I highly recommend, if you have time, do it yourself. Download a bunch of these historic temperature measurements and fit a deep neural network or an artificial neural network. I think with a hidden layer of size, I think it was larger than 20. So a hidden layer is this unit here, these neurons which are in between the input and at some point we have the output. So this is a hidden layer and it had more than 20 neurons in this hidden layer, so a rather large neural network, and it was able to perfectly fit the training data. However, it was completely flat. It told me that the it gave a predictions for minus temperatures. So let's say I have a new data point which has minimum temperature -5, and it would give me still prediction y hat 0 because it's flat here. The deep neural network didn't care at all on the behavior, about the behavior for feature values outside the range of the training set. So it looks perfect on the training set, but outside the training set, it's telling me basically that the maximum temperature will be, or it predicts the maximum temperature with 0, no matter if the minimum temperature is -5 or -30, which is completely unrealistic. However, this is unrealistic for us because we have a lot of prior knowledge on how the temperature behaves. So what is the nature of minimum and maximum temperature? With our knowledge, we would expect that the predicted temperature should go down if the minimum temperature goes down, and also that the maximum temperature should go up if the minimum temperature increases. So we should not have this flattening out here. This is completely unrealistic. However, for us it's unrealistic because we have a lot of prior knowledge and concepts about how weather behaves, but the computer doesn't have that. So the computer is stubborn and just fits the deep neural network weights, so it tunes these parameters. It tunes these parameters to perfectly fit the training data. And it's very successful in this regard. It fits the training data perfectly. However, it doesn't generalize well. So it doesn't generalize to new data, which is different from the training data. And then one key message of this course was to show you how to detect such a scenario. So how can we detect such a scenario? How can we detect if the training error 0 is not really good? So even if the predictor achieves training error 0, it is not a good predictor. How can we find that out? What is the basic technique to find out if zero training error means that it's really a good predictor? Yes, very good comment from one student. We have to split the data. So let's see, we have again this data set. And we split the data, and ideally we split it randomly. So we take this one, we take this one, and we take these two. We split those two, and we say this one is the training. And we fit a model or a predictor function on this training subset. So we fit it on this. And if we use, again, a deep neural network or a polynomial with high degree, it will perfectly fit the training set. So we will get zero training error. A deep neural network, for example. But if we look at the remaining data points, which we call the validation set. So this here is the validation set. And for this, we will have a large error. So we get a large validation error. So the important thing is always to compare the validation error with the training error. So the training error might typically be very small, in this case even 0. So this is the training error. And if the validation error is much larger than the training error, then this is a hint that we might overfit the training data. And what can we do to cure this problem or to avoid this problematic scenario? Overfitting is bad. It's maybe the most challenging situation in machine learning, or one of the most important goals in machine learning is to detect overfitting and to avoid it. So how can we avoid overfitting? How can we bring this validation error down, so to say, even if we need to sacrifice a bit more training error? Well, one reason for overfitting could be that the hypothesis space is too large. There are simply so crazy nonlinear functions in this hypothesis space which perfectly fit any training data. So what we could do is reduce hypothesis space by using simpler predictor functions. So what could be a simpler function than highly nonlinear polynomial or neural networks? What is a simple function? Does anyone have an idea? What are simple predictor functions? Well, in my opinion, one simple function is a linear function. It doesn't contain too many parameters. So we could try to fit a linear function here, which incurs some training error. So the training error is not 0 anymore. However, the validation error goes down. So the validation error here becomes smaller. So using a smaller hypothesis space, for example, the space of linear functions is a subset of the space of polynomial functions, since every n-degree polynomial contains linear functions as a special case obtained by setting all the weights of higher powers to 0. So the space of linear functions is a subset, is a smaller space than the space of polynomial predictors with a large degree. let's say degree n 100. So using simpler functions like linear functions helps to avoid overfitting. And this is also another reason for using linear functions. Not only we can fit linear functions easily using gradient descent, they are typically not so sensitive to incur overfitting. Okay. Okay. Other options to reduce the training error or to reduce the validation error at the risk or at the expense of increasing the training error a bit. So it's not the absolute size of hypothesis space which is important. It's always important the ratio of number of parameters or weights but to the number of training data points. This ratio is important. And here we can reduce this ratio. What we want to is to bring down this ratio. We can reduce it either by reducing the numerator, use predictor functions with less parameters, which means reduce the hypothesis space, or we can try to increase the denominator, use more training data. But this might be challenging because getting training data means you need to know the labels for data points. And if it's not a time series problem or a problem which is somewhat stationary over time, we expect for this temperature prediction problem, we expect the relation between morning minimum temperature and maximum temperature during the day to be somewhat similar over the last 30 years. I mean, we will have some effect of global warming, but still, roughly speaking, the relation between minimum and maximum temperature stays the same. Whenever you have such historic label data, it's easy to get more training data. However, in some applications, it might be very challenging to get training data because training data, in order to get training data, you need an expert, for example, a doctor, a lung expert in the case of diseases, which needs to look at an X-ray photograph and give the label or give his or her prediction of the label. For example, does this patient have a certain infection or not? So using more training data might be more difficult than just reducing the hypothesis space, because reducing the hypothesis space means you have to adapt one line of Python code. Instead of using a polynomial regression, you use the linear regression class in scikit-learn, for example. So that's why maybe this first option is more popular. Okay, so this was now a rather compact walk through one application of machine learning, where we discussed how to model a problem or an application as a machine learning problem. The application was finding out the maximum temperature for a nice ski day ahead. And we can implement this as a machine learning problem by defining a data point as being some ski day, which has features obtained by the Finnish Meteorological Institute. The label is the maximum temperature of the day ahead. And we try to find a predictor based on historic data that we can obtain from the Finnish Meteorological Institute. And then we try to fit different types of predictor functions. And we don't need to, by the way, you don't need to do this by gradient descent yourself. This is the nice thing about Python. Instead of using gradient descent to find the optimum, finding the optimum is exactly what this .fit function does. For example, for linear regression or for decision trees. Whenever you hit the .fit function, Python libraries compute or try to find the optimal choice for the weights. Yeah, so you fit the predictor function to the data set, but then it's important to also look at the validation set to make sure that the predictor is not does not overfit to the data that you have. Okay, so that was rather a compact walk through the basic concepts of machine learning that I tried to teach while in this course. Are there any questions now?